Welcome to episode 26, Compute Options Overview, VMs, Containers, Functions, where we frame the practical landscape of how Azure runs code. Compute is the engine of the cloud. It is where instructions turn into action. Azure offers three main styles: virtual machines for full control, containers for consistency and portability, and functions for responsive, event-driven tasks. Each model trades flexibility for convenience in different ways. Knowing how they relate lets you match the right one to the right problem instead of defaulting to habit. Imagine choosing between owning a house, renting an apartment, or using a hotel. Each suits a different stay. By the end of this episode, you will be able to picture where each compute model fits and what operational rhythm it demands. Virtual machines, or VMs, remain the most familiar compute form in Azure. They provide complete control over the operating system, installed software, and network configuration. A VM is ideal when you must run legacy applications, custom drivers, or complex stacks that do not fit higher abstractions. For example, a manufacturing system relying on a specific Windows library can lift and shift directly into Azure with minimal code change. The trade-off is responsibility. You manage updates, scaling, and backups yourself. That control attracts administrators who want predictability but requires discipline to maintain security and cost efficiency. In short, VMs are versatile but heavy. They reward precision and punish neglect. Managing VMs brings operational overhead that shapes long-term strategy. Each instance needs patching, monitoring, and lifecycle care just like a physical server. Automation tools such as Azure Update Manager or desired state configuration help, but the responsibility stays with you. Scaling means provisioning more VMs, configuring load balancers, and sometimes handling image drift. For small systems, this overhead feels manageable. For hundreds, it becomes a challenge. Imagine maintaining 50 VMs, each with slight differences. It becomes hard to know which one failed and why. This overhead is the reason many teams look for ways to abstract compute, seeking agility without giving up necessary control. Containers shift focus from machines to applications. They package the code, dependencies, and runtime environment into lightweight, portable units that start quickly and behave consistently everywhere. A developer can build a container image once and run it on any host that supports the container runtime. This eliminates the "it works on my machine" problem and accelerates deployment. In Azure, services like Azure Container Instances or Azure Kubernetes Service host these workloads. Containers fit modern development where microservices, rapid iteration, and CI/CD pipelines dominate. They blend flexibility with efficiency, but still need orchestration to manage scaling, networking, and resilience when used at scale. Container orchestrators handle that complexity, and Azure Kubernetes Service, or AKS, is the flagship option. It automates deployment, scaling, and health management across clusters of container hosts. Kubernetes enforces declarative control. You describe the desired state, and the system reconciles reality to match it. Alternatives like Azure Container Apps or managed platforms such as App Service simplify this further by hiding most cluster operations. Choosing among them depends on how much control you want versus how much maintenance you can afford. AKS is powerful but complex, while serverless containers and apps trade deep configuration for speed. The right balance depends on your team's maturity and workload sensitivity. Serverless functions represent the lightest and most abstract compute tier. An Azure function runs only when triggered by an event, an HTTP request, a message in a queue, or a scheduled timer. You pay only for the time your code executes, not for idle servers. This model excels at bursty workloads like image processing, scheduled tasks, or IoT event handling. Developers focus purely on logic, while Azure handles provisioning and scaling behind the scenes. The trade-off is limited runtime duration and less control over the environment. Serverless shines when agility and cost efficiency matter more than fine-grained tuning of the infrastructure beneath. Scaling differs sharply among these compute models. Virtual machines require manual or scripted scaling, where administrators decide when to add or remove capacity. Containers use orchestrators like Kubernetes that watch load and scale pods automatically within defined rules. Serverless functions scale instantly in response to incoming events, sometimes from 0 to hundreds of instances in seconds. Each approach suits different rhythms. Predictable traffic fits manual scaling, fluctuating demand fits orchestrated scaling, and spiky workloads benefit from serverless. Understanding these patterns prevents both under-provisioning and overspending, ensuring compute adjusts as naturally as workload intensity does. Startup time, or cold start, becomes a key experience factor, especially for serverless and containerized environments. A cold start happens when no instance is active, and the platform must initialize code before responding. Azure mitigates this with warm pools, preloaded environments that keep functions ready to fire instantly. Containers also experience startup delay based on image size and complexity, while virtual machines have the longest boot times but stay warm once running. Planning around these differences matters for user experience. A chatbot using serverless functions might cache warm instances to avoid lag, while batch jobs can tolerate slower starts. Awareness turns delay into design rather than surprise. Handling state across compute models reveals philosophical differences. Virtual machines can store state locally, making them straightforward but harder to scale horizontally. Containers should be stateless whenever possible, persisting data to external storage to allow flexible scaling and quick recovery. Serverless functions rely on durable storage services or databases to maintain state between executions. This separation of compute from data allows rapid elasticity, but requires intentional design. Imagine an order processing function that logs transactions to a queue and writes to a database. Its reliability comes from decoupling state rather than keeping it in memory. Clear state boundaries build resilience regardless of model. Cost patterns across compute choices depend on runtime, scale, and management effort. VMs charge continuously for allocated capacity whether used or idle. Containers usually cost for underlying compute nodes and storage, offering better density when optimized. Serverless functions charge only per execution, often saving money for intermittent workloads. Yet cost also includes operational labor. Patching and monitoring VMs consumes people hours, while serverless shifts those costs into service fees. A thoughtful cost comparison accounts for both money and time. The cheapest model on paper can become expensive if it requires constant manual care to stay reliable. Security boundaries differ across compute tiers and define who patches what. In a VM, you control and must secure the operating system. Containers share the host kernel, so you patch base images and manage isolation carefully. Serverless removes nearly all infrastructure patching, but still requires secure code and dependency management. Understanding these divisions prevents blind spots. For example, running outdated container images undermines the benefit of a managed orchestrator. Azure provides tools like Defender for Cloud to track vulnerabilities across models, but responsibility still aligns with control. The more freedom you have, the more maintenance you must own. Observability also shifts with abstraction. VMs rely on traditional monitoring agents that collect logs, metrics, and traces from inside the operating system. Containers benefit from centralized logging and distributed tracing that capture activity across microservices. Serverless functions emit telemetry automatically through application insights, but you may need custom correlation to link events end-to-end. The goal is consistent visibility no matter how ephemeral the compute is. Metrics like request count, duration, and failure rate unify these worlds. Building observability early avoids blind spots when workloads move between models, ensuring that troubleshooting remains possible even when infrastructure is invisible. Choosing the right compute model becomes clearer when matched to workload traits. Stable, long-running systems with strict configuration needs lean toward virtual machines. Distributed, fast-changing applications favor containers for flexibility and portability. Event-driven or unpredictable workloads thrive with serverless functions. The decision also depends on team skills, compliance rules, and expected lifetime of the application. A hybrid approach is common core services on containers, integrations on functions, and legacy components on VMs. Evaluating compute is less about fashion and more about fit. Each model offers a different balance of control, cost, and simplicity. Understanding Azure's compute spectrum brings confidence to design choices. Virtual machines embody control, containers embody consistency, and functions embody speed. Each sits on the same platform but speaks to a different rhythm of change. When you align workload behavior with the right model, operations feel smoother and scaling feels natural instead of forced. The goal is not to pick one forever, but to know when to switch as needs evolve. With this perspective, Azure Compute becomes a palette, not a constraint. Each option a tool for building resilient, efficient, and modern applications. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.